Group number 11. Copper. Copper has two oxidation numbers that are more or less common. Most common is 2 plus with configuration 3d9. Copper 1 exists with 3d7. Total number of valence electrons in copper is formally 11, because group number 11. But you never have oxidation numbers larger than 3, so removal more than 3 electrons from copper is rather difficult. One may suspect some analogy between group number 1 and 11. There is analogy, but very, very limited. Of course, copper, like elements of 1, is metal. Oxidation number 1 is stable. There are several beautiful minerals of copper, 2 of them, 2 different carbonates of very similar, slightly different formulas, are shown here. They are bright green malachite, known for numerous artworks made with it, and azurite, fantastically beautiful blue pigment. Historically, they were used as copper ores, but not now. They all are mined out, and whatever samples you can find are used for art purposes mostly. Copper can be found naturally as elemental in Old World, in Asia, Africa, and Europe. Most of natural copper was mined 1,000 years ago. In North America, next to Lake Superior, you still can find some deposits of copper, which are fantastically beautiful and interesting. Nevertheless, the most common form of copper we are using for production is sulfide minerals. So, a common process of copper manufacturing for last 8,000 years is starting as smelting process. Copper sulfide is oxidized to copper oxide, which in turn decomposes into metal copper and oxygen. Well, this is an example of modern smelting furnace, which is just first step of lengthy manufacturing process. In old days, this would be the last, because it will result in very impure metal coming out. So concentrate of ore and sand is coming into furnace, and admixtures of iron, and usually they are up to 50% of iron in copper ore, are mixed with silica, making iron silicate, FeSiO3. Copper still stays partly as oxide, mostly as sulfide. On the bottom, much heavier and separated. Copper iron sulfide, chalcopyrite, is one of the most common modern copper ores. It has its golden look. It was mined 1,000 years ago. It's still mined now. An example, the world's largest Bingham Canyon mine in Utah. which is almost 1 kilometer deep hole in mountain. Copper production is only one part of this enterprise. It also produces silver, gold, palladium, platinum, molybdenum, lead, and lots of sulfuric acid. So the process will be, first you are getting copper concentrate, removing necessary impurities, then run smelting furnace, so sulfur burns to SO2 that is collected. Whatever copper sulfide is lead goes into converter furnace, then it burns further to get copper metal. Again, SO2 is collected and goes to sulfuric acid plant. So you have your first product, H2SO4. Then you make crude copper in a anode furnace, after which you cast anode of your electrolytic purification. So you have your anode and you put it into electrolytic device. So what happens here? At one electrode, blister copper anode, you dissolve copper. At pure copper cathode, it's precipitated as pure metal. It looks like this, as a pure metal. And now it's very important to collect not slime. These are impurities, but they are very important for further processing. So slime is collected and goes into slime treatment plant. You have silver, you have gold, you have palladium, platinum, and other admixtures. It provides with a large part of income from this enterprise. If no side products like sulfuric acid, molybdenum, gold, and so on, Bingham mine would not be economically feasible. Copper can be used as pure metal, mainly for wiring, but mostly we make alloys. Most of them have generic name, bronze, which has 80 to 90% of copper, 20 to 10% of tin, maybe up to 10% of zinc, and lots of different components. Contrary to iron alloy, it never has visible amounts of carbon. Brass is slightly softer alloy, more household, that contains lots of zinc and less copper. There are plenty of other copper-containing alloys in use. Metal copper does not react with hydrochloric acid or diluted sulfuric acid or diluted phosphoric and so on without oxidizer. But it reacts with nitric acid and concentrated sulfuric acid with no water. So concentrated nitric acid reacts with copper to give NO2 gas and copper ions as nitrate. And these are beautiful crystals of copper nitrate. When you use diluted nitric acid, reaction will go to nitrogen monoxide. With concentrated sulfuric acid, you will have copper sulfate and SO2 gas. So in all cases, you have Cu2+. Cu2+ has electron configuration of 3d9, So there is only one position here at which electron stays. And of course it can be here or it can be there. These two orbitals have exactly the same energy. Young-Teller effect splits it into two different. So you do not have octahedral complex. You have slightly elongated octahedron with splitted energy levels. So coordination number can be 6, but in fact it is 4 plus 2. Two other ligands are slightly different than 4. We can look at example of very beautiful ammonia complexes. Copper compounds are blue, but ammonia complex is very deep blue. So you are adding step by step ammonia molecule number 1, number 2, number 3, and number 4. You will have a large difficulty to put more than 4 molecules around one copper. But this is not the end of the story, because there is still one water molecule staying in this complex compound, which theoretically could be replaced by ammonia. And you can see the colored compound. Copper 1 has electron configuration of 3d7, so complete d electron shell. No d-d transition possible because all orbitals have 2 electrons on them. That means Cu plus compounds will be colorless or close to colorless. You can make halogenide of copper 1. For example, chloride can be made by reaction of SO2 and water. So CuCl with low solubility will precipitate, leaving sulfuric acid and HCl. You can use usual sugar or glucose to reduce copper chloride with the same result. You'll have white precipitate like this of CuCl with such crystal structure. You see that's tetrahedral environment of copper atoms. Same is true for bromide, exactly the same. Reaction of copper with iodide goes on addition of iodide ions to Cu2+. You cannot have Cu2+ in presence of iodide. Cu colorless precipitates and iodine is released. Copper iodide has cubic structure with larger coordination numbers. A little surprised because iodide is larger.